I Am a Bug by Robert Sabourin, illustrated by Catherine Sabourin. A children's book about software testing. Meant to be read by children from 3 to 8 years old. I am a bug. Here are some people who care about me. Bugs are not good or bad, but some bugs are important. And some bugs can cause an awful lot of damage. A mosquito bite may not hurt so much, but a swarm of mosquitoes can be dangerous. A bee sting may hurt quite a bit, but it can kill you and can be really, really bad if you're allergic to bees. Bugs like to hang out in damp, messy places full of bugs. But bugs are also found in the neatest homes and the cleanest yards. The neatest homes and cleanest yards. Some bugs sleep for a long time. Long time. And surprise, we're lucky to get a butterfly. The cocoon became a butterfly. Our net can catch butterflies easily. We can catch butterflies with our net. But not our old friend the mosquitoes. The mosquito's too small to fit in our net. What net should we use to catch bugs? We've got to get the right net to catch the right bug. When you get stung by a mosquito, what do? You swat it and you scratch. It's not necessarily good to scratch. Scratching soothes the pain, but it doesn't really solve the problem. Maybe medicine can work better. Maybe you could put some lotion on to make it better. Insect spray can also help by keeping the bug away from us. We can spray to keep the bug away from us. But it doesn't help much if there's a whole swarm of bugs. When you have a whole swarm of bugs, the spray doesn't seem to work too well. We can put nets on. Nets can keep mosquitoes out of the way. So we put a net on our head to keep the mosquitoes away. And some people make fancy zappers. They're machines, zappers, to help with the bugs. Zappers look really cool. They're fancy. They're beautiful. They look really cool. But they really don't keep the bugs away, because the bugs can figure out how to avoid the zapper. You see the bug is turning off the switch, turning off the zapper. So be careful. The tool looks like it'll help you, but sometimes it doesn't. Spraying insecticide might be a solution. Insecticide. Avoid the bug. Insecticide. That might be a solution. But more than the mosquitoes can get hurt, the insecticide can hurt a lot of people. Birds can get hurt. Animals can get hurt. All different people can get hurt from insecticide. So even though insecticide can get rid of the bad bugs, it can hurt a lot of other things too. Maybe we could change the environment. Maybe we could landscape to get rid of the swamp with our tractor. Landscape to get rid of the swamp. Maybe that'll help us get rid of the bugs. Or maybe we can move further away from the woods to live somewhere far away from where the bugs are. Of course, you can always just stay inside until wintertime, right? And in wintertime, we don't have a whole lot of bugs here. I'm from Canada. It gets very cold. Not too many bugs outside in the winter. We can use smoke to get the bees out. So if you put smoke, the bees go away. And we can take our rugs and shake them outside to get rid of the bugs that are hidden on them. We can fumigate a house. We could take our whole house and put a big tent over the house and fumigate it to get rid of the bugs once and for all. That's a really strong way to get rid of the bugs. Spiders make webs to catch bugs. So what's interesting is spider can catch a bug with a web. Frogs like bugs. See, a frog likes a bug. So if you want to get rid of a bug, why not get a frog? And the frog will eat the bug. The frogs eat the bugs. They love to eat the bugs. And they can only eat so many bugs. They can't eat all the bugs. They can eat a lot of bugs, but they only eat a few. So that means that you need a lot of frogs. Bugs try to avoid frogs. So the bugs see a frog, they run away. They're afraid of the frog. Bugs can disguise themselves with camouflage. So the bug can hide in the tree and look like a leaf. So it's disguised like camouflage. But so can frogs. So frogs can look like rocks or something. They can hide. So they can hide from the bugs. Getting lots of frogs can help get rid of lots of bugs. But then you've got a problem with too many frogs. And too many frogs in the same place are a big problem too. What do you do when you find a bug? What do you do when you find a bug? That's a good question. What do you do when you find a bug? Collect it in a jar with holes on top to look at it. How did we catch it? Is it important? Can it hurt us? What are we going to do? What are we going to do? Well, some bugs are good friends. And some bugs are okay as long as we stay out of their way. If we step on the anthill, maybe that'll keep the ants away. Maybe we can do that. That's very specific for that type of bug. Maybe we can step on the hill. The thing is that when I step on one hill, they go and make another one. So that's only good for a few minutes. Living with ants is not that bad. One ant's not a bad thing. Ants are not that bad. But if you have a picnic on the table instead of the ground, you're okay. But if you have the picnic on the ground, there's all the ants there. If you must get rid of them, if you must get rid of bugs, if that's your job to get rid of bugs, you should do it well. Do it well. Get rid of them. Do it well. Be professional. Do it well. You know you're finished. You know you're finished. You know you're finished when the only bugs left are the ones you decide you can live with. So you see that people are looking at the bug, at least for now. At least for now. So that's I'm a bug. Let's look at I'm a bug read from the parent's perspective. So first, to make our job more fun, whenever we have a problem with software, we call it a bug. Audrey is our QA director. Her team finds the bugs. Yves-Alain is our development lead. He makes sure bugs don't get into our software, but if they do, his team gets rid of them. And Oliver is our product manager. He works with our customers to find out what our programmers should do. Oliver helps us decide which bugs to get rid of and which bugs to keep. When a bug is found, we do not ask the question, is it good or bad? We decide if it's important, and we guess how much damage it could cause. We take care of important bugs right away. We take care of important bugs right away. And we always look out for dangerous bugs. We're always looking out for dangerous bugs. A lonely little bug may not look too dangerous, but hundreds of little bugs at the same time can be very dangerous. The same bug can be found in different programs. In one program, a bug may not cause too much damage. But in another program, that same bug could be fatal. Fatal. When we rush too much making new software, our offices and our programs can get pretty messed up, pretty sloppy, pretty messed up. And we know there are going to be a lot of bugs. So when we rush too much, we know there's going to be a lot of bugs. When we take our time and when we are tidy at our work, our offices and programs are neat and clean. But we may still have a few friendly bugs. We don't get rid of all the bugs just because we're neat and clean. Sometimes we find bugs a long time after people start to use the programs. We say that these bugs were asleep. So sometimes a bug waits a long, long time. Once in a while, a sleeping bug wakes up. And if we're lucky, it doesn't cause any damage. And when a sleeping bug wakes up, sometimes we call it a feature. When we test computer programs, we make a test plan. A test plan is like a net to catch bugs. Some test plans only catch really big bugs. Some test plans work better to catch small bugs. Sometimes we use one test plan to catch the big bugs, and then if we have time, we use a finer test plan to catch the smaller bugs. So you catch the big ones, then if you have time, you catch the smaller ones, and if you have time, you catch the even smaller ones. When bugs can be fixed in a simple, straightforward manner, we feel only a minor irritation. Minor irritation caused by bugs can often be fixed by changing how people use the software. So if you change how you use the program, then maybe you can avoid being irritated by the bug. One time we found a great way to avoid a very, very special kind of bug. It was a fantastic way to avoid it. But we found out that this very special bug had about 1 million brothers and sisters. And we knew a lot of tricks to stop bugs from getting into our programs in the first place. So like a net. A couple of years ago, a fancy pants salesman sold us a new and exciting toy called the Bug Zapper. We were convinced that all our bugs were going to be gone forever. So this is a tool to help us catch our bugs. At first, the Bug Zapper seemed to get rid of some pretty important bugs, but it didn't take long for the smarter bugs to figure out how to avoid the zapper. We couldn't even get our money back. We have to be very careful when we fix a bug. When we fix a bug, we might break something else by mistake. When we start a new project, we think hard about how we can avoid getting too many bugs. Should we start with a clean office with fresh new ideas? We try new ways to make our programs, new methods, new tools, new techniques. When we're not sure what to do, we can sit back and wait till things calm down. Don't rush. Wait. Maybe things will settle. Then we'll get the job done. We use many ways to get rid of bugs. We can scare them away. When we scare them away, they don't die, but they get out of our path. We can shake things up a bit until the bugs fall to some other place. The bug's still there, but it's not in our way. It's best to get rid of them once and for all. We fix them and make sure they cannot move someplace else. My friend James used a trick called assertions to catch bugs whenever they passed by in his programs. So assertions like a spider net, right? That will catch a bug when it goes by. People at work think positively about bugs. We like to find bugs. When we find bugs, we really like to fix them. We fix bugs one at a time. When we fix a lot of bugs, we divide them up between many people. Naturally, when we try to fix a bug, it tries to avoid us, right? The bug tries to go away. Sometimes we cannot even see a solution to a bug, even if we're looking right at it. The bug is hiding. And sometimes we have to be very sneaky and hide, waiting for the bug to show up. Once we decide to get lots of people to help us correct all the bugs, once we decided to get lots of people to help us find and fix all the bugs. But they didn't help because we got all mixed up and confused. It was hard to keep organized. When we find a bug or a bunch of bugs, we all get together and have a bug review meeting. We study the bugs very carefully. And we look, how did we find the bug? Whether we have to fix it right away, and how much damage can it cause? If we're lucky, we can keep the bug in our program for a long time. If we use the program in a different way, we will avoid some bugs completely. Sometimes plugging the hole ants come out of just moves the problem to somewhere else. Before we decide to keep a bug in our program, we must remember how the program will be used. How are you going to use this program? When we decide to get rid of a bug, we proudly fix the bug. We professionally double check to make sure it's really gone. The most important question we ask ourselves is whether we have finished our work. Is it time to let someone else use our program? Can we ship it now? We look at the bugs we see in the program and ask ourselves how important they are and how much damage they could cause. And the bugs take a good look at us too. We know our job is done when the bugs that are left are the ones we can live with. At least for now. So stop testing and get some sleep, folks. Good night. The third reading of I'm a Bug is from a software engineering perspective. I encourage people working on software projects to have a very broad concept of what a bug is. I like to define a bug as any concern someone has about the project. Many people try to use a very specific definition of a bug. One is to say that a bug is a defect, a problem, or an anomaly in the software injected into some artifact, like a requirement or a design of the code or something like that, either by omission or fault characterized by failure in the software. But a bug isn't always caused by a defect or an error. Sometimes it is just an emergent behavior. It emerges. So this definition limits what a bug is. So important concerns may go unreported. Broadly speaking, any concern about the project, I like to consider that a bug. At least for the purpose of this book. Let's try that. There are three significant perspectives necessary on the triage team to make a decision. These perspectives are provided by the SQA director, the development lead, and the product manager. In a triage meeting, the triage team decides whether to fix a bug or not to fix a bug. Deciding to keep a bug makes the bug part of the product. This decision is usually made when fixing a bug could do more damage than not fixing it. Keeping a bug makes it part of the product. Usually customers must be encouraged to avoid or ignore it. A bug triage meeting should involve a small, effective group of people. Small, effective group of people who are qualified to make decisions largely on their own. A bad bug triage meeting involves a large, ineffective group of people that keeps calling more people into the room because they can't make a decision. Even a good triage team may sometimes need additional input, but very rarely should they pass the responsibility of making the decision of whether to keep or fix a bug to someone else. So that's the triage. The SQA director is the advocate for the QA perspective. The triage team looks at the bug using objective information provided by the SQA director. Then the development team and the product manager discuss the information and reach a decision. The SQA director does not vote on whether the bug should be fixed or not, but she should be impartial. Now, the development lead is the advocate for the developers. His job is to assess the technical risk of fixing or not fixing a bug. And the product manager just get this up here. Product manager is an advocate for the customer. His job is to assess the business risk of fixing or not fixing a bug. If the product manager and the development lead are always arguing about which bug to fix and which bug to keep, I usually err on the side of the product manager because he is the best positioned to know the needs of the customer. The importance of a bug, its priority, and the amount of damage it could cause, its severity, are independent. Priority and severity are assigned separately. The priority and severity of remaining bugs is often the ultimate decider of when the software will ship. Therefore, the people setting the priority and severity of the bug hold a powerful position, one that should not be held by summer interns, as I have seen far too often. Testers may propose priority and severity, but this isn't the final say. Each bug fits into one of 4 quadrants. Quadrant 1 for high priority, high severity. Quadrant 2 for high priority, low severity. Quadrant 3 for low priority, high severity. Quadrant 4 for low priority, low severity. A healthy understanding of the number of bugs testers are finding in each quadrant can help in the evaluation of the effectiveness of testing efforts. If a lot of bugs are being found in quadrant 3 or 4 instead of quadrant 1 or 2, the testing team should perhaps test another part of the program instead of, or use different testing techniques. Some bugs are important. How can you tell if the important bug? How can you tell if an important bug is important? Answer: the bug is wearing a tie. Some people might say it's also wearing it has a briefcase. How do you tell if it's an important bug? It's carrying a briefcase. The classification of priority is a business decision. It's a business decision influenced by people, resources, timing, and so on. A minor bug in a part of the program deemed extremely critical by stakeholders may have a high priority but a low severity. The priority of any given bug may actually change if the business or technical context changes. A bug that was important last week may not be important this week. If the customer have decided that they no longer need a particular feature, a bug that had a high priority the day before may not even be relevant anymore. Those who decide bug priority and severity should be acutely aware of the business context. They should know who the stakeholders are, who the customers are, what the technical constraints are, what the design drivers are, and so forth. Then they should use this knowledge to alter their view of new bugs if necessary and to update their view on old bugs. Priority and severity depend on context. Some bugs can cause a lot of damage. Dangerous bugs that are bugs of high severity. These are bugs that could crash the program or even worse, destroy data or be harmful. As with priority, the severity of bug can change over the project due to changes in business context. Severity can change too. A lot of bugs in a program can aggravate user and even make the program unusable, even if each bug by itself has a low severity. Or a low severity bug with an easy workaround might generate many support calls if it affects a lot of users. A grammatical error in a help system won't hurt anybody and might not even be noticed. In medical software, a grammatical error can have a more devastating effect than a system crash. If a medical software crashes, the doctor won't use the diagnosis and no one will be hurt. But if a grammatical error, such as confusing the past and present, takes place, they could make a difference between life and death in how a decision is made in studying the patient's medical history, for example. So we have to be very cautious. The exact same type of error could in some contexts be fatal. Bugs like to hang out in damp, messy places. Poor software engineering practices produce a swamp like the one shown here, and all sorts of bugs can flourish. Fixing bugs is a business decision, and sometimes there is little benefit or no benefit to be gained by fixing a bug. A friendly bug is a bug that does not stop users from enjoying and benefiting from the software. Just because it doesn't conform to the requirements doesn't mean it's bad. Sometimes a feature that enhances users' experiences with the software may be a bug because it does not conform to the requirements. Other friendly bugs can be little nuances in the program that weren't intended but don't bother users. The AVT 710 patient record software had lots of bugs, but people could avoid them. Even with these bugs, it was a reliable product with 0 field reported defects. So we had a product with a lot of bugs, but they didn't bother anybody. At the time the software was written, the bug was there, but it did not become apparent until later when the context of the software changed. An example is Visio 97. It was originally designed at a time when hard disk space was much smaller than it is now. But trying to install Visio 97 on a newer computer with lots of disk space, and the installer says there's not enough disk space for Visio to be installed. Why? Because Visio 97 used 32-bit arithmetic to calculate free space, and that worked fine at the time it was made, but new computers have a large amount of hard disk space that it cannot calculate in 32 bits. Due to round-off errors, the truncation of the calculation is bogus. The bug was dormant for many, many years and was exposed by the evolution of technical constraints over time. Sometimes the way in which the software is used changes over time. For example, Windows printer drivers for the LaserJet 2 printer were designed to print out forms. The code in the drivers cannot handle printing out color photos. These drivers work fine in their day, but would not work now. Or software might migrate between user communities. Software meant for specialists might one day be used by Joe Public, and the two communities have very different interests, needs, and a bug that wasn't a bug for the specialist might be a very important bug for Joe. All right. When bugs wake up, they become characteristics of the system, like it or not. When a sleeping bug wakes up, it can cause backward compatibility headaches if users have become used to the bug and depend on it being there. A classic example is the margin calculation in Microsoft Word, which was incorrect in older versions. When Microsoft fixed the bug, all files from the previous versions had slightly skewed margins on the new version. So this is, by fixing a bug, they had a huge regression, backward compatibility problem. There are test suites called FAST, where FAST stands for Functional Acceptance Simple Test. This test tests every capability of the system once with normal data to gain confidence that the system can handle normal inputs, but it doesn't guarantee that the system handles anything else. It's like a different type of test plan. Test plan can focus on different granularities of bugs. Depending on the time and budget for testing, sometimes it's better to explore as many risks as possible, but not too much depth, as opposed to testing each risk in great depth. The finer the net, the greater the depth of testing. Bugs can be fixed, avoided, or ignored. If a bug won't be fixed, users can be encouraged to use the software in a way that avoids the bug. There are special techniques to find specific bugs. A good example is self-verifying data checks. For specified inputs, the software can be checked against the testing oracle. This is an excellent way to find data integrity bugs. A technique for finding buffer overflow bugs may be very good at finding buffer overflow bugs, but they would be useless for finding calculation errors. Bugs much worse than buffer overflows could be walking right by. Similarly, checking for data integrity bugs through self-verification techniques is not time or cost effective if there are a lot of user interface bugs or the business logic bugs preclude the ever reaching the data in the first place. These so-called tricks include 3 critical workflows in software projects: configuration management, requirement management, and test management. They include development discipline, static analysis, inspections, peer reviews on checked-in new code, unit testing, good development practices, good architecture, and a whole host of other things. These are the tricks we know to stop bugs from getting into our programs in the first place. Salespeople from tool vendors sometimes misrepresent the cost and benefits of tools and their ease of use. For example, they may claim that a test automation tool that can capture actions and play them back will solve all your problems. They say, take this tool and you can write a program that will find all your bugs. This sounds attractive at first, but these type of tools require a very large amount of programming and don't really solve any problems. They also make maintaining a test a nightmare. Tool vendors may also claim that a requirement tracking tool will reduce costs, but the tool itself will not save money. What will save money is having the discipline to manage the requirements. This is the pesticide paradox. If the same testing technique is used over and over again, the bug the test technique targets will disappear, but other bugs will find a way to survive. Don't rely on only one technique or tool. Sometimes the solution is worse than the problem. The solution to a bug may create or reveal other strange behaviors in the system, or the bug may be fixed perfectly on the functional level, but quality factors like performance, reliability, availability, and maintainability, and so on are compromised. It's important to pay attention to the 3 fundamental workflows of software engineering: requirement management, configuration management, and test management. If these are attended to and fully understood, there will be far fewer bugs due to sloppiness. There will still be bugs, but they will be the kind of bugs that should be there. Bugs caused by project risks and poor project management, for example. Trying new techniques and new ways to work around problems is a double-edged sword. For instance, to avoid having to develop a high-risk piece of software, sometimes people will trust third-party middleware. This avoids the development problem entirely, but results in a lot of integration problems with other software. Sometimes the best thing to do is to step back from the project and look at the big picture. Instead of hunkering down and coding while there are still lingering concerns, take the time to understand the requirements and identify helpful technologies, tools, skills, and processes. Otherwise, you can get stuck solving the wrong problem. There are times when a project shouldn't even be undertaken. Once I helped formally inspect a development plan against its requirements, and so many discrepancies were found that the project was canceled. That project shouldn't have been started in the first place, and it wouldn't have been if they had taken the time to understand the problem first. Sometimes it's a good thing to expose as many bugs as you can to be aware of their existence. You might not be able to isolate them or fix them until later, if ever, but you know that they're there somewhere. For example, some companies try a dramatic approach called a bug bash. Before the release of the product, employees work over the weekend to expose all the bugs by whatever means they can think of. The bugs probably won't be fixed or even isolated before the product's release, but the company will know the bugs are there. Noel Nyman invented a technique called monkey testing, a random testing technique that explores random parts of the application and does random things to smoke out any bugs. This test can be, and usually is, done automatically and can find odd bugs that a human tester may never stumble upon. Assertions tell whether a program is in the state it should be during execution. Whether a file is opened before it is written, if the assertion is violated when it should not be, the developer knows there's a bug. For unit testing and sometimes early system testing, assertions can be very useful for finding bugs quickly. However, assertions do not make business decisions. If they are violated, they stop the program's execution. For later system testing, this means a minor bug could halt testing until it is fixed. So assertions shouldn't be present by that stage. Assertions are even less appropriate for a release in commercial systems. Whether or not a given bug should be fixed depends on business context. Just as a frog's stomach can only contain a finite amount of bugs, a development team doesn't have the time, effort, or money to fix all the bugs found in a program. Bug priority and severity need to be established based on a cost-benefit analysis to figure out which bugs are worth fixing. The cost of not fixing a bug can be the damage to the user's computer, the number of support calls generated by a bug, damage to company's reputation, and so on. Just a few of the potential drawbacks of fixing a bug are the danger of injecting or uncovering more bugs, a developer's time and effort spent, and the chance of decreased adherence to quality goals such as performance and availability. There are several different ways in which bugs can camouflage themselves. One way is to hide in plain sight. Take, for instance, a bug that brings up an error message before login. During testing, the testers learn to ignore it on the login of the system, almost unconsciously clicking it away. This is why it's important to retest a system once a bug has been fixed to make sure that no other bugs have been unearthed. For example, in a database system, a bug that returns an incorrect query could be canceled by a bug that reports queries incorrectly. Some bugs are best caught by system monitoring. This is dynamic system monitoring. For these bugs, monitoring agents like Bounds Checker can be set up to watch the system and flag bad behavior, including inappropriate access to system resources, memory, and memory leaks. There are other bugs that can be found through explicit testing. To find browser compatibility, just test the software as normal while varying the browser, and browser compatibility bugs will very often just pop up. Bringing in more testers to work on a project can be a nightmare. Any training needed will result in a temporary dip in productivity. The mythical man month will come into play, and management requirements will increase to the point there will be no productivity gain at all. Sometimes it's better to provide a workaround for a bug instead of fixing it. This is especially true if there's no time for regression testing, because fixing a bug could reveal more bugs. Quick patches don't solve problems. Fix it right the first time. Think about how the program will be used. The exact same program can be used by many different people in many different ways. And a bug that is a deal breaker for one user community may be inconsequential for another. Regression testing is used to make sure the bug is really gone and no others have sprung up in its place. I find the fundamental question of software engineering is, how do you know you're finished? Many developers start developing without knowing the answer to this question. Some answers to the question are better than others. Unfortunately, some developers consider themselves finished when they have to go home. They catapult the code over the next phase in development. They find that this results in poor software quality. It is far better to answer the fundamental question using information gained from requirement management, configuration management, and testing. The answer to the fundamental question may involve ensuring some particular degree of code coverage, some static analysis or quality factor like usability, reliability, or maintainability. But in order to ask the fundamental question, the exit criteria must be accurately defined and widely understood. For example, unit testing answers the question, am I finished implementing this unit of code? Is it ready to be passed along to someone else? If unit testing is sloppy, it may be, and often is, because the developer doesn't understand what the purpose of the code is. Thus, when the developer uses unit testing to decide if he's finished with the unit of code, he may be making the decision based on the false assumption of what it means to be finished. This is why I want everybody on a particular project of a specific task within a project to have a common notion of what the answer to the fundamental question is. This way, everybody knows that what their role in the completion of the task is going to be. Well, that's the end. Hope you enjoyed that. Thank you.